Hey, we're going to talk today about Beer's Law. Um, Beer's Law it's a weird thing because it's not something we're going to use a whole lot, but it may come up on the AP exam. Um, so Beer's Law deals with concentration, and one of the ways that we measure concentration is by using a spectrophotometer and applying the Beer-Lambert Law to it. I call it Beer's Law just for short. It's shorter, easy to say, but it's actually Beer-Lambert. Um, and so Beer-Lambert is just multiplying three things together. The path length, which is usually the width of the little cuvette test tube that you use. The molar absorptivity, which is something that you look up, for a certain concentration, you've got a certain molar absorptivity. And then the concentration, which is what we want usually. And then when you multiply those three things together, that gives you the absorbance. And so when we're talking about absorbance, if we plot the absorbance, we can get the concentration back out of that. Um, and no, it's not something we're going to use a whole lot. We will talk about concentration in our lives at certain points. You may have to mix up a solution to feed your tomato plants if you're a gardener, and you need to have the proper concentration. If you're going to clean your house or clean, power wash stuff, you need to be able to dilute the chemical, or the chemical will cause your paint to peel, and it'll be a huge mess. And then, if you really want to get serious about it, you might have to mix up medicine for your kid, or in my case, something that's much closer and near and dear to my heart, my dogs. So if you don't know how to talk about concentration, you're not going to be able to um, properly mix those chemicals, and we don't want to talk about negative outcomes. But what I thought is I found a couple of problems on Beer's Law, and hopefully you'll be able to read this. So what I want you to do right now is you can pause this and read it. Okay. So I'm going to read through the problem, and then I'm going to read through the choices. So the diagrams show the ultraviolet absorption spectrum for two compounds. There's the absorbance that we're talking about there. Diagram 1 is the absorption spectrum of pure acetone, a solvent used when preparing solutions for an experiment. Diagram 2 is the absorption spectrum of the solute for which the absorbance needs to be measured to determine its concentration. When the student reads the absorbance of the solution at 280 nanometers, the result is too high. Which of the following is most likely responsible for the error in the measured absorbance? Okay, they're messing with us really hardcore. So this, and what you need to look at here is this is a different scale than this. This is kind of a blow up. And so if this is your acetone, you see right there at 270, you see that little hiccup? That's that hiccup right there. Okay? So our choices for this one are: the student added too little solute to the acetone before measuring its absorbance. Okay, that would not cause the absorbance to be off. The student rinsed the cuvette with the solution before filling the cuvette with the solution. The student forgot to calibrate the spectrophotometer first by using a cuvette containing only acetone. The wavelength setting was accidentally changed from 280 to 300 nanometers before the student made the measurement. Well, when you look at it, you have this hump here that shouldn't be there, and it's that hump there. So we're looking for something that involves acetone because they give us the spectrum of acetone. We don't know anything about the solution, so it's hard to talk about the solution. The student added too little solute to the acetone before measuring its absorbance. A lot of people would probably pick that. The student rinsed the cuvette with the solution before. That would cause maybe, but the reason is it's too high at 280. So D is out because it goes to 300. I would say the answer is C. And the reason why I say the answer is C is because they talk about acetone. They give us that acetone graph, and we see that acetone likes to absorb at 280. It has that little hump there. And since it has that hump at 280 and it's too high at 280, that indicates that it's probably the acetone is absorbing and the solution's absorbing. And so that's kind of the problem there. So the answer to that one is C. That is the hardest one we're going to do. A student uses visible spectrophotometry to determine the concentration of cobalt chloride in a sample solution. First, the student prepares a set of cobalt chloride solutions of known concentration. Then the student uses a spectrophotometer to determine the absorbance of each of the standard solutions at a wavelength of 510 nanometers and constructs a standard curve. Finally, the student determines the absorbance of the sample of the unknown concentration. Okay, so I'm going to give you that paragraph right there. So you can stop and read that paragraph. And then a student made the standard curve above. Which of the following most likely caused the error in the point that the student plotted at 0.050? Okay, so here's our plot, and there's the point there. It's too low, and immediately when we're dealing with this and the absorbance is lower than what we would expect, I'm looking for something with water. Something has diluted this, okay? So my choices are, there was distilled water in the cuvette when the student put standard solution into it, and this is most likely. There were a few drops of the 0.100 molar cobalt chloride standard solution in the cuvette when they put 0.05. That's not going to work because the 0.1 would have caused the dot to go jump up above because it would have been more concentrated than the 0.05. So for B. The student uses a cuvette with a longer path length, again, because Beer's law is that absorbance equals absorptivity, path length, concentration. I don't know why B is path length. I just don't know. But if you use a longer path length, that's going to give you more absorbance because, think about if you have 1 centimeter here, which most of them are 1 centimeter. If you do 2 centimeters, that's going to double the answer, double the absorbance, and the absorbance is going to jump up. So C, not good. D, the student did not run a blank between the 0.05 molar and the one before it. Once you've run a blank, you don't need to run blank after blank after blank. Once you've run a blank and you know what the background is, So I said if it's low, we're looking for distilled water. We're looking for something diluting it, and there's A right there. A, distilled water. The distilled water in the cuvette diluted that solution. Okay. Number 3, using a spectrophotometer, a student measures the absorbance of 4 solutions of copper sulfate, copper 2 sulfate, at a given wavelength. The collected data is given in the table above. Which of the following is most likely explanation for the discrepant data in trial 4? Okay, so look at that. And we're looking at trial 4 there, and there is discrepant data. And so I want you to pause, and I want you to think first what that discrepant data is. It's a discrepancy. It's something we shouldn't see. Okay, now that you're back, Here are the possible reasons why that data was discrepant. And what was discrepant, you may ask? You might not know at this point. What's discrepant is, look, from here to here, it doubles. Here to here, it basically doubles, and here it doesn't double at all. So the discrepant data is at trial 4 at 0.150 molar, it doesn't double. It doesn't go up as much as we'd think. So here are my possible choices. The solution was at a lower temperature than the solution in the other trials. Who knows? The measurement was made using a different spectrophotometer that uses a cell with a longer path length. Again, that would cause higher absorbance because the path length would be longer. It would double the, however much longer the path length would be. And the solution was saturated and the flow of light through the solution was restricted. If it was saturated, nothing's getting through. Mutual absorbance, like absorbance to infinity. The concentration of the solution was lower. So, if it's lower than 0.15, the absorbance is going to be lower than we'd expect. So, maybe somebody didn't make the right solution, and it was actually lower than 0.150 molar, and so the answer for that one is D. Solution was actually lower than we thought it was, and therefore the absorbance was lower than we thought it would be. And that's what I have for you for today on Beer's Law.